Hello Hassan, this is going to be my presentation for the first part of the book, Computer Systems, a Programmer's Perspective. So let's get into it. The book in its first part just kind of follows a Hello World program through all its cycles from the source code all the way to assembly and then to the last part, and it uses that as an example to explain the kind of general architecture of a program. And essentially goes something like this. You have the CPU, which is made up of registers and arithmetic and logic unit, plus the central command part. You have your main memory and the connection systems and the other parts of the computer. The main issue you have here is that the computational speed of the computer is way faster than the connection time with the memory. By the time the connection has passed, the computer may have made up to 300 computations, and this is a problem. And for this, you kind of have various levels of memory. You have the main solution is the cache memory, because it's a cache, and it's kind of it's a sequential retrieval rather than a random retrieval, and it's faster. Obviously, registers are just kind of like placeholders for the CPU, and then you have your memory. The further you go up this, it gets faster, smaller, and costlier. Obviously, it's the inverse when you're going down. Moving on, the system kind of the book kind of explain what are operating systems, which are essentially just a bridge between the hardware and the user, and they operate like an abstraction layer. And there are three main parts the book talks about. There is the fact that files acts like an abstraction layer for the I/O, the input-output centers. The processes act like an abstraction layer for the CPUs and everything else, and the virtual memory acts an abstraction layer for the actual hardware memory. That's about it. And then the kind of moves second part, which is the kind of most important part. Obviously, just going back, why this is important is because if you understand this, if you understand the hardware and understanding all the layers above it, it's much easier. You can much better pinpoint where problems are, and you kind of have you understand how things are going on under the hood, and this means you can write excellent code. The book moves to the idea of how a program represents data. The basic idea is that it represents as bit codes. The book uses hexadecimal because it's human readable, and it's different from decimal. So it's kind of has a educational value. But the essential idea is that the computer has various bytes, and each byte can be interpreted in many different means. Can become a decimal, can become an ASCII code, can become a different kind of code depending on the tables. But the essential idea is that you have bits, and the context is what turns them into usable information. The book then moves into the various ways or kind of talks about how integer representations kind of dictate the arithmetic. He talks about the two's complement, which is very important. Essentially, every bit here, like the sum of these bits here, are representing this bit plus 1. So if these here, I assume they mean 1, 2, 3, that's to the power of, yes, I think they mean 64. This one is going to be 65. But if it's positive, it means negative, so it's negative 65. And you essentially do the sum of them. So you do this is 0, so it means nothing, but in here it's 1, so this means minus 65 plus whatever is here, and you get the output here. I'm not going to go into details about this, but I'm just going to kind of give you how this can be useful. Before the two's complement, there is something called the one's complement, and let's take just 4 bits to explain. So essentially, this bit is what representing the sign. If it is negative, it means the number is positive. If it's 0, the number is positive. If it's negative, the number is if it's 1, the number is negative. And essentially, you have 3 bits to represent your number. So you have 2, that means that's 7, plus positive, negative, that means you have from minus 7 all the way to 7, that's 14 numbers. But on 4 bits, that's 2 to the power of 4, that you can represent 16 numbers. So there is a number missing. And the idea is that you have -0 and +0, and that obviously causes problems because it can overflow. You can do an operation and it overflows and you get a different number than the operation would. And while this can be avoided if you're doing the computation yourself, but a computer cannot avoid that, and this causes problems. So what they did is they added the two's complement. So this one is it does not just signify the sign, it also signifies an extra number. So it goes in the case of 4 bits, it goes from -8 all the way to +7, rather than from -7 to 7. And the general idea is that you are trying to represent an infinite number of integers using a finite number of bits, and that obviously causes problems. And the only way to avoid issues in your programming is to kind of be mindful of this and be mindful in your programming. Obviously there are some insights, some ready insights, like the basic stuff, like if there is a -1, it means that all of the bits are 1, because this is essentially this +1, but it's minus. But the main idea is that there is a philosophical mismatch. You are trying to represent an infinite number of numbers using a finite number of bits, so there has to be problems, and you have to account for that. As for the floating numbers, the floating numbers are represented using the IEEE Association standard, which means the Institute of Electronics Engineers or something like that. But essentially there is an exponent, the mantissa, and the sign. The mantissa is the actual number, and the exponent is the power of 10 for that number. For example, you can represent 100 as 1 multiplied by the power of 3, and in that case the mantissa is 1.00 and the exponent is 3. The sign is obviously the sign. And this is, once again, you have the same problems as the problem in the two's complement, because this is not a problem of specific representation, but it is a problem of arithmetics in computer science itself. Arithmetics in real world uses real numbers which are infinite, but arithmetics in computer science does not have the means to represent an infinite number. So if the number keeps growing, it essentially just cuts off the bit that this cannot represent in its available finite resources, and you have to account for that in your program. Obviously there are some insights you can use for just to derive from this idea of programming to kind of understand where problems can be. You can read this as you wish, but the main idea is to understand that there is a fundamental difference between arithmetics in the real world and in computer science. This has been my presentation. Thank you for watching.